This webcast talks about circular orbits of satellites and also the energy of satellites. Isaac Newton was the first person to think about what would happen if an object actually reached an orbit around the Earth. He thought about firing a cannon, and he knew that if you fire a cannonball with a greater velocity, that it's able to go further before it hits the ground. And in his mind experiment, because he couldn't do this physically, but he could think about it, he thought, well, if I achieve higher and higher firing velocities for this cannonball, eventually the cannonball will never fall to the ground. It will actually travel all the way around the Earth. And that type of projectile, where an object moves around a central body, in this case we're thinking about a cannonball moving around the Earth at its center, when an object moves in a circle around a central body, it's called a satellite. And the trajectory and the path that the object takes is called an orbit. The picture here is actually an illustration from Newton's book. He drew this. So this mind experiment is called Newton's cannon. And basically, he was saying that the faster a cannonball is fired, the further it will travel before falling to the ground. And since the Earth is circular, it's a sphere, if you go fast enough, then the ball will keep falling around the Earth and will never actually reach the ground. This website has a simulation of Newton's cannon. And so here is Newton's drawing of the Earth, and he imagined a mountain with a cannon on top. And so the initial speed that the cannonball will be fired at is 3,000 meters per second. Okay, I'm going to fire it. Okay, so even though that's pretty fast, 3,000 meters per second, the cannonball traveled some distance, but it did fall down to Earth. Okay, the reason it fell is because, right, anything that you drop or fire falls to the Earth because of the gravitational force that's pulling it back toward the center of the Earth. Okay, let me increase the speed a little. Let's go to like 4,100 meters per second. Okay, so with a faster firing speed, the cannonball was able to go further before it hit the ground. Let me go a little faster. Let's go up to 6,000 meters per second. Okay, we're going further and further, but we still aren't getting into orbit yet. Let's go a little faster. 7,000 meters per second. Oh, look at that. It went a good distance around the Earth, maybe a third of the way or a little bit further. Okay, but still not going all the way around the Earth. Let me go up to 7,800. Oh, look here. The cannonball is moving. It's falling around the Earth, and so it made it all the way around without ever falling to the ground. That might have been a little faster than I had to go. Let's go to 7,400. And so I had a slower firing speed, and so it didn't get quite as high above the Earth, but it still got into orbit. Okay, so that's a picture of Newton's cannon. So a satellite in circular orbit is moving along a circular path. And in order to move in a circle, and we've talked about this, there has to be a centripetal force that keeps pulling it toward the center of rotation. For a satellite, that centripetal force is the force of gravity. And if there were not a force of gravity that the Earth is exerting on the satellite would just move in a straight line, right? There wouldn't be anything to make its direction change continually. So a satellite is in continual free fall. The only force acting on the satellite is the force of gravity that the Earth is exerting on the satellite, pulling it back toward the center of the Earth. So the satellite is continually falling, and it has to be going fast enough in order to fall around the planet and to stay in orbit. Okay, so here is a picture of this. This is referring to, a man-made, a robotic satellite in orbit around the Earth. The force of gravity, F sub g, is the centripetal force that keeps the body moving in a circle. In this picture, you can see the gravitational force pointing from the satellite down toward the center of the Earth. I'm also showing the velocity vector, the tangential velocity. Notice that's not a force, right? That's just to show you that at any point in time, the tangential velocity is changing direction. Okay, so the centripetal force, S sub c, is the gravitational force in this situation. And we know the formula for centripetal force is the mass of the satellite multiplied by the square of its tangential velocity divided by the radius of its circular path. And since that centripetal force equals the gravitational force, I'm setting that equal to uppercase G, the universal gravitational constant, multiplied by the big mass, that's the mass of the planet, multiplied by the little mass, that's the mass of the satellite, divided by the square of the orbital radius. Okay? Notice that the smaller mass cancels out. If I divide both sides by the lowercase m, it goes away. And so I've taken a couple of steps to solve for the tangential velocity, and I see that for a circular orbit, the tangential velocity equals the square root of g times the big mass divided by the orbital radius. And that orbital radius is the radius of the Earth plus the altitude of the satellite. An interesting thing here is that the mass of the satellite, that was the lowercase m, the little m, it canceled out. That means it's irrelevant in determining the velocity of a satellite. Okay, so this is an important equation here because it will allow us to calculate the velocity of a satellite in a circular orbit. So the speed of an object in circular orbit around a central body with a mass of big M is determined solely by the orbital radius. And we say that because the planetary mass, the big M, is going to be pretty constant. And also, of course, the universal gravitational constant, the big G, is constant. In a circular orbit, the speed is constant. So everywhere that the satellite is moving, it is going at the same speed. Now, it is accelerating because its direction is continually changing, but its speed is not. The satellite is in uniform circular motion. And so if the speed of the satellite changes, well then its orbital radius will change. Or vice versa, right? The lowercase v and the lowercase r, these are the only variables that are changing. Big G, big M, these are constants. And so if the velocity changes, the radius has to change. If the radius changes, the velocity has to change. Okay, so here is an example. What is the speed of a satellite in circular orbit 500 kilometers above the Earth? Okay, so I'm finding I'm adding the radius of the Earth plus the altitude to get the orbital radius. Okay, and that has to be in meters. And then I know big G is 6.67 times 10 to the negative 11th. I'm multiplying that by the mass of the Earth. It's the big mass that applies here, the mass of the central body. And then I'm dividing by the orbital radius. I take the square root of that, and I see that that satellite, 500 kilometers above the Earth, is moving at 7,610 meters per second. So a satellite has both gravitational potential energy and kinetic energy. It has kinetic energy because it is always moving, right? It's always moving in a circular path around the Earth. And it has gravitational potential energy because of its position. It is high above the Earth, and so it has some gravitational potential energy. As the satellite moves closer to the Earth, the gravitational potential energy gets smaller, right? It is falling, and so as it falls closer to the Earth, the gravitational potential energy gets smaller, but it has to move faster, and so its kinetic energy gets bigger, increases. Okay, the total energy of the satellite is constant, and that total energy is the sum of its kinetic energy and its gravitational potential energy. The energy is constant because the system that consists of the satellite and the central body, here we're talking about the Earth, there are no external forces on that system, and therefore there's no way for work to transfer energy either into or out of it. Remember, when we talked about energy, we said that the energy of an isolated system is constant. Well, the satellite and central body is a system that's isolated, and so its total energy is constant. Now, one interesting difference for satellites is that we have a different reference point for where we say that gravitational potential energy is equal to 0. You know, previously, when we were talking, mostly about things on the Earth, we said, well, the ground or the floor, that's where EG is 0. But when you're talking about satellites, the reference point where that EG is 0 is defined as an infinite separation, meaning the satellite is infinitely far away from the Earth. And as the two bodies approach each other, the potential energy decreases. It's decreasing from 0. That means it is always negative, and it becomes increasingly negative as it gets closer to that central body. So just saying it again, the gravitational potential energy is always negative for satellites. So here is the equation for kinetic energy of a satellite in circular orbit. And we're using, the same equation that we have used for other objects' kinetic energy. We're taking half of the satellite's mass and multiplying it by the square of its velocity. But the velocity of a satellite is the square root of gm over r. And so when we square that, we get gm over r. And so anyway, the kinetic energy of a satellite, shown in blue here, is always the gravitational constant multiplied by the mass of the central body, that's the big mass, multiplied by the mass of the satellite, that's the smaller mass, divided by 2 times the r. The r is the distance between the satellite and the center of the central planet. Now, the gravitational potential energy of a satellite, we can also take that, derive that from the equation we're used to for gravitational potential energy, right? We've always used mgh, the mass multiplied by the acceleration due to gravity multiplied by the height. Okay, but in this case, the gravitational potential energy equals 0 when the orbital radius is infinity. And so the potential energy is always going to be negative. The height is the distance of the satellite from the central body. That's the orbital radius, r. And so if we take that formula, we're going to make it negative because of the way we've defined the 0 point for gravitational potential energy. So it's going to be negative m times the acceleration due to gravity, which is gm over r squared, and then multiplied by the orbital radius. And so we get that the gravitational potential energy of a satellite is negative g times the big mass times the satellite's mass divided by the orbital radius. If you compare these two formulas, you can see that the kinetic energy of a satellite is always positive, but it has half the value of the gravitational potential energy. The total energy of a satellite is equal to the kinetic energy added to the gravitational potential energy. And when we add those two things together, we get negative gmm over 2r. Notice that the total energy of a satellite has the same value as the kinetic energy, but it is always negative. So the total energy of a satellite in circular orbit is always negative. And so here's just a summary of these formulas to find the kinetic energy, the gravitational potential energy, and the total energy of a satellite in circular orbit. So energy is required if you want to move a satellite further away from the Earth or whatever its central planet is, because the total energy of a satellite increases as the radius increases. And so if you move the satellite into a larger orbit, a higher orbit, it takes energy to do that. Okay, and so you can find the amount of energy that you would have to spend to change that orbit by looking at the difference in the energy between the final orbit. It would be the energy at the final orbit minus the energy at the initial orbit. And we're talking about the total energy at those orbits. And so that is negative gmm over 2r. So this looks complicated, but what you could do is calculate the total energy at the final radius and then subtract the total energy at the initial radius. Even though both of these quantities are initially negative, when you subtract them, you're going to get a positive amount of energy because it requires you to invest energy to move a satellite to a higher orbit.